Today, I would like to talk about linear rather than exponential decay in red blood cells, mathematical model and underlying mechanisms. This was actually a little project I did together with my dad, and I'm very excited to talk about it today. So the motivation. Well, the motivation for this particular project was my curiosity. I was working on a drug that seemed to be affecting red blood cells, and so I wanted to quantify the dose-response relationship between the drug and red blood cell decay, as I would typically do. But I discovered that my typical approach does not work here. And that is because RBCs do not die exponentially, like all self-respecting populations. Instead, they die linearly, and then only do this like maybe a little exponential thing at the very end. Well, and that turned out to be surprisingly difficult to capture with a continuous function. So while that particular project, that particular drug didn't go anywhere, the question of how to capture linear rather than exponential decay really stuck with me. And that's what I'm going to try to explain today. So typically, when we're talking about models of population extinction, we are typically describing them with exponential decay. So the decrease in population size is proportional to the number of individuals currently present in the population. This is a very typical equation. N prime equals minus k times n of t. K is a parameter. So as I said, n is population size, changes over time, k is the per capita death rate. But this does not work for RBCs. I started digging a little deeper, so I looked for more data. So here, for example, in this Mock et al. Paper from 2019, the authors labeled aliquots of autologous RBCs from healthy volunteers, and they tracked proportion of circulating labeled cells by flow cytometry over 20 weeks. So if you look at all of these here, they are looking pretty linear. RBC survival in subjects followed a pattern of extinction that is much more closely captured by a linear function rather than exponential. As I mentioned before, even in the previous one, maybe a little bit of exponential decay at the very end, but it's really linear. Okay, so how do I model this? What do I do with this? Well, there's a brute force approach. You could just say, oh, n prime of t equals minus k, and that may fit the data in early stages, but of course soon it predicts negative population size, unless I introduce some kind of a mechanistic switch. Numerically, if I say if n of t is 0, then everything below that is 0. I do not like introducing mechanistic switches. They are not elegant. I like finding continuous functions. So I found that mathematical representation of linear death rate using just a single model, a single equation, presents a very surprising challenge. When I look through the literature, so when I look through people who try to model RBC decay, they used it using PDEs. They did it using integrated differential equations. But a single ODE model that can actually successfully describe linear population decay, to my knowledge, when we were doing this, does not exist. Or does it? Dum, dum, dum. Okay, so what's the model? Consider population of extinction given by our n prime equals minus k n, but now to the power p. That is, instead of our typical p equals 1, let's take p to be less than 1, between 0 and 1. And so let's look at how changing kind of the three main parameters, we can capture the different shapes of this. Okay, so let's change initial population size, n of 0. I mean, that one is pretty clear. Just changes where you start. So, but still, it's a parameter. It's important. Now, much more interesting here is changing parameter p. Okay, let's look at this. So, if p is large, okay, so you're getting much closer to your exponential situation. As it decreases, this flattens out and flattens out and flattens out and is starting to look suspiciously linear as p decreases. Okay, so that's kind of nice. And then if you change parameter k, so this rate of decay, okay, so if it's really large, again, population dies very quickly, kind of makes sense. And as it is decreasing, okay, flattens out, flattens out, flattens out a little more. Although the linear doesn't look as linear as when you decrease p, but still, it extends it. Okay, Turns out, with just this simple model, we can easily fit the RBC data. So I digitized some RBC data from different papers and just didn't even need to do any particular fitting. Could just manually vary these parameters and find very, very, very good fits that describe these data, or very good ways to describe these data. And then I confirmed it using fminCon in MATLAB. Okay, so there is an alternative approach to get to the same kind of functional forms through explicitly calculating time to extinction. It's in the paper. I'm going to give a link at the end, but I personally like working with ODs, so this was my method here. Okay, so we have the phenomenology down, but now the next question. Is it just phenomenological, or is there maybe an interesting underlying mechanism that would make sense for why this particular functional form would describe linearly decaying populations? Well, one possible way to infer an underlying mechanism would be as follows. We can rewrite you remember this one, n prime equals minus k, which I really disliked. We can rewrite it as n prime equals minus k times n divided by n. Okay. So if each individual then in this population has their own individual death rate, then the population can be subdivided into these subgroups, subpopulations. We call them clones, L to V, where each individual is characterized by their own value of parameter A. So we're starting to look like this. Okay, that's interesting. Total population size is then given by the sum of all of these clones. So it makes sense as well. Or if it's a continuous function, then it's an integral. And then, so this is something you will need to follow up and look into the publication here. It takes a little while to describe, but we proved in this paper over here that the power law n prime of t equals minus k n to the power p describes the frequency dependent model, so this one over here, which we derived from over here, if the individual death rate parameter comes from a gamma distribution. Oh, I know. Okay, I'm going to go through this a little closer. So we propose that linear decay can be the result of natural dynamics of a population that is heterogeneous with respect to individual death rates. If the cells had the same death rate, the population would decline exponentially. Now that they have different death rates, and if these death rates fall within the gamma distribution, then when you look at the total population dynamics, so sum up all of those subpopulations, you actually can get this kind of a linear decay. And it can be described by a sub-exponential model n prime of t equals minus k n to the power p. That is a population where each individual, in this particular case, individual cell, is characterized by its own value of its own death parameter, and where cells die proportionally to their frequency in the population, we call them F models, frequency-dependent populations, will exhibit linear decay. So that's pretty cool. But what does it actually say about underlying mechanisms? Well, to think about that, I would like to go back to actually frequency-dependent model of population growth, because that's really how I was thinking about it. I remember seeing in frequency-dependent models of population growth that we might have an exponential phase followed by a linear phase. So here you can actually confirm it with a log transform. So here, see in this section, you have linear, so this is exponential growth, and then it stops, it changes. So I was thinking, well, what if you slap a negative sign on there? What if instead of growth, you have a decay? Won't you get the linear exponential decay? And yes, you do. And so if you think about these F models of growth, where this comes from, in these models, subpopulations with different individual growth rates grow proportionally to their frequency in the population. Okay, so one interpretation of this structure in, again, growth models is that total population growth is proportional to access of different subpopulations to some resource. For example, we were thinking in terms of cancer cells, it can be maybe access to blood vessels. So different subpopulations have different access to the resources. Now, if you put kind of the negative sign on it, maybe what you see here is different subpopulations have different We called it some kind of a death resource. I understand this is not really a good term. Can't think of a different one, but if you think of it mirroring the growth ones, so different subpopulations basically maybe get damaged at different frequencies or die at different rates proportional to their access to this quote-unquote death resource. So, and it's the absence of such resource can make individual cells more susceptible to elimination. Okay, so what kind of resources could be? Well, one can speculate about such death resource is maybe this comes from the RBC life cycle. So it starts in the bone marrow from hematopoietic stem cell progenitors in the process called erythropoiesis. Okay, and after some maturation steps, cells called reticulocytes, and they enter circulation, then they mature into erythrocytes after about 2 days. And then they circulate around the body for approximately 120 days and become removed if they age or become damaged. The removal can occur in the spleen, in the liver, in the bone marrow. They can be removed by macrophages that break them down, engulf them, and like releasing iron stores from cells, so together with other factors that can stimulate further erythropoiesis. So essentially, we're thinking, well, maybe this rate of removal due to these external factors, they don't have their intrinsic death, they have this extrinsic damage. Maybe that would be our quote-unquote death resource. So how does it fit with the model? As I was saying, within the framework of the proposed model, maybe that some cells suffer uneven damage as they circulate through the body. So the physical aspects of the space that they encounter during their life cycle would become this death resource. I really should think of a better name. Maybe somebody else has a better idea. And it could be some other external factors, maybe exposure to phagocytic cells, any kind of access to something that will make their death non-uniform. And that would provide a mechanism for why RBC death would be not density, but frequency dependent. Of course, this is a hypothesis, needs to be evaluated, design a good experiment. Maybe somebody else can do it. The fact that lifespan of RBCs actually doesn't seem to be fixed. So we've seen that it's shorter in infants rather than adults. And it's affected by different conditions, such as change in altitude and even space flight. So this, in my opinion, can support the hypothesis of these external resources regulating cell survival. But again, remains to be evaluated. Also, kind of an interesting thought experiment, maybe there are more populations that are subject to linear rather than exponential decay, but we are just not seeing them. Like we didn't see the lens to see and describe it. And maybe we thought, oh, it's just a badly fitting exponential or something. But this proposed model actually provides this possible mechanism that may explain such dynamics, this frequency-dependent decay. So we wrote this up in a preprint, kind of didn't get it through to the full publication, it was too much effort. But I would love to talk about it. Does this interpretation make sense? If you want to chat science, please reach out. I'm always happy to chat science, talk about possible experiments, how do you test the hypotheses. On my side, I'm just glad I found a function that can describe those suckers because it was driving me crazy. And now, whenever I deal with a project that has linear decay, maybe something RBC related, I know how to model it. And now so do you.